So we're going to look at 4.8, number 7. We have this function, f of x equals the square root of 49 minus x squared, which this is a circle centered at 0, 0 with radius 7. And I'm going to integrate it from minus 7 to 1. So I'm really looking, oh no, I'm not integrating, sorry, I'm jumping ahead. I just want to know at what point, so let me just, from 7 to 1. So if I was to graph this for a minute, this is a semicircle centered at 0, 0 with radius 7, and I'm going from minus 7 to 1. So if I plug in 1, I have this point here. So I have the slope of the secant line. So I'm expecting my slope to be positive. So let's find the slope of the secant line. I take f of 1 minus f of minus 7 over 1 minus minus 7. So f of 1 would be the square root of 48 minus 0 over 8. So this equals the square root of 48 over 8. Right? So it's positive, so that's what I expected from my picture. And I'm saying, what point in this interval, some C point, where the slope of the tangent line is parallel to this slope of the secant line? So I take the derivative of the function. Let's plug in C, because that's the theorem. It's saying there's some point C here. So I take the derivative, which would be 1/2 49 minus x squared to the minus 1/2 times minus 2x. So really I have x over the square root of 49 minus x squared, and I'm setting that equal to the square root of 48 over 8. It would be negative x. Thank you. I dropped that negative. So now at this point it's algebra. So this problem, the application of the theorem isn't too difficult, but the algebra of actually getting what this x value or the c value is, and I said c here, then I wrote x. I'm really bad at a habit of that, and if you guys do that, it's perfectly fine. It's looking for, and you can call it x, you can call it c, you can call it any variable you want. It's just some value in this interval. X is just a placeholder for that. So at this point, I'm looking for when minus x, the square root of 49 minus x squared equals the square root of 48 minus 8. Sorry, divided by 8. So if I multiply both sides by the square root of 49 minus x squared, that cancels. Then if I square both sides, I'm left with x squared equals 48 over, I think, 8 squared, 64, thank you, times 49 minus x squared. So then I have x squared equals 48 times 49 over 64 minus 48 times x squared over 64. So if I add 48 over 64 x squared to both sides, I would get 48 plus 64, 12, 6, 7, 8, 9, 10, 11. 121 over 64 x squared equals 48 times 49 over 64. So if I multiply both sides by 64 over 112, I get x squared equals 48 times 49 divided by 112. So if I take the square root of both of those, it gives me plus or minus value. So that could be to take into account, and I have to look at my range to see what's in there, but what do we get here? We get 48 times 49 divided by 112. So the square root of 21 equals plus or minus the square root of 21. The square root of 21 is about 4. So from our interval, only the minus one would make sense. So my answer here would be minus the square root of 21. Whew.
if we have decimals in a problem on the final, we're probably doing it wrong.
Probably.
Okay.
Yeah. If it gets, I mean, so here enter the exact answer. So I'm looking for negative square root of 21. Granted, I did the algebra correct, which is right. So you can always kind of see the solution here, and it's going through all the things that we did. They probably simplified their numbers a little earlier. I didn't necessarily. You don't have to do that, but.
So just using, because I looked at this solution and using all the C's instead of the actual numbers was just kind of throwing me off. I didn't know how to follow it.
What it means is it drives specifically from the notation the book uses, saying they don't want to call it x, they call it c. There's some point in the interval they name it c. So if you take the derivative and plug in that c, you're setting that equal to the secant line, the slope of the secant line. So here we did this, or we essentially did this in terms of x, and then said we're finding an x value, which x would be the c value we want. So it's kind of weird, the book. Every semester I'm like, oh, I'm going to write C every time. And then I revert back to X. It's a really bad habit. But I don't think it necessarily, you know, if you have C's, that's fine. If you're just so used to working with X's, you can work with X and at the end say, this is your C value. This is the specific value, and C means something. C is the value that the slope of the secant line is the same as the slope of the tangent line at the point C. You're looking for that C value. But you don't have to deal with C until really at the end and say, okay, this is C.
As far as the difference between the rolls and the mean squared, is that just the rolls, the two x values you're given when you plug them in to find your f of x's, they equal 0, is that correct?
Rolle's
So
theorem is a special case when the slope of the secant line is 0.
Okay, and so you find your derivative, set it equal to 0, and that would be your c.
That will be your C value.
Whereas with the mean
Value theorem.
value theorem, you're gonna have to plug in those to find your slope, set it equal to your slope.
Yes.
Right?
Yeah, you find them the slope of the secant line, you set that equal to your derivative, because that's where you're saying, when does the derivative equal the same slope as the secant line? That's what you're looking for. The special case when the slope is negative, or sorry, when the special case when the slope is 0, you're looking for the point in the interval in which you have a slope of 0, which would be a maximum or a minimum, which we've had a lot of experience about doing that. Here we're just looking for, this is not a maximum or a minimum, it's just the point C in the interval in which it has the same slope as the secant line between -7 and 1. So if you change this problem from, -7 to 7, it becomes an application of Rolle's theorem, right? Because the slope between -7 and 7 is 0. So the point C would be 0. X equals 0. Or C equals 0 here, because the slope at x equals 0 is parallel to the slope of the secant line from -7 to 7. So you could almost kind of like move this down and see how this one also moves with it. It's moved around.
So for Rolle's theorem, does the x value have to be, or does the y have to be on the x-axis?
No,
Okay.
it can just be any
Horizontal.
yeah. So if this was an x-axis and this was my function, I could say that.
And that's Rolle's.
And this is Rolle's theorem. But it's also, Rolle's theorem is a special case of the mean value theorem. It is also the mean value theorem, but more specifically when the slope of the secant line equals 0, we call that Rolle's theorem.
And for those two, you'll have a polynomial, right? that you can-
Yeah, because the hypothesis of the theorem is the function is continuous, right? You can't have any jump. So rational function you could have if it was on a specific interval, but you have to make sure that it's continuous. Once you verify it's continuous, then you can apply the theorem. So here the algebra was maybe a little higher level than solving for a quadratic or a linear expression, but
How do you show that it's continuous?
if it's a polynomial, it's continuous. So you can just, so you really don't even have to show it's continuous, you just have to note it's continuous.
Okay, we don't have to
Like
write that.
continuous, yeah. You have to check it.
Alright.
And that's something that's saying, oh, every polynomial is continuous. A rational expression, if I have something like 1 over x minus a, this is continuous everywhere except at a. So then if I said, you know, from 1 to 5, let's say this was 10. This is continuous on 1 to 5. Right?
Yeah, it's a closed interval, but inside that interval, it's
From
It goes
minus
on
infinity
past.
to infinity, it's not continuous. It's not continuous from 1 to 12 because it contains the point of discontinuity, which is 10. So verify it's continuous. Yes, it's continuous on 1 to 5. Any polynomial is going to be continuous everywhere, anywhere. It's always going to be continuous. Question?
I have a question on integral. When we have like x over something like x minus a number, how do we integrate that?
Like this?
Like, yeah, well, we have x at the top and x at the bottom.
Like just x over x?
Minus something or plus.
Like x over x minus 1.
Yeah.
And all this is over 1?
Except the
No,
minus
like-
1 is in the
Is in a
denominator.
denominator.
Like this?
Like, yeah.
Don't you take the x minus 1 to the minus 1 and then multiply it by x?
You can't do that. You can't have like x to the x minus 1 to the minus 1 and write x squared to the minus x to the minus 1. That's illegal. Well, one attempt you could do here is do a u substitution. U is x minus 1. Du is dx, and then x is u plus 1. So you have u plus 1 over u. Right? So then you can write this as 1 plus 1 over u, which would be u plus ln of the absolute value of u. If you plug that back in, what is in terms of x, you have x minus 1 plus ln, the absolute value of x minus 1. So that's a little bit higher level than where we're at right now. Where'd this come from?
I saw it in the online YD
In for
in 5.2.
5.2.
The question with respect to
And that's u
Like
substitution.
the homework.
no, not the homework, like the reading,
wasn't the homework.
read study stuff.
Oh, it was assigned in the homework?
No, the read study.
But I assigned it?
No, it's not in the homework.
Yeah. Yeah, it was just, but it wasn't when I assigned.
No.
Yeah, so this is doable. It's a u substitution, but we're not quite to the point where you might have something like this on the final, but the u substitution. We're not quite there yet, though, because I don't really like the way the book introduces integration. Today, I think it's going to make more sense, because we just came up with this idea of, okay, now you need to find a perfect function that you differentiate it, you get what's in the integral. That's the antiderivative. That was the whole idea in 5.2, right? It's saying if I integrate capital F of x dx, I get smaller case f of x plus c. So if I take this function and differentiate it, I get this function. So they're like kind of working backwards at first. And then they say, okay, now that you've got used to working backwards, you can work backwards by doing u substitutions. So you could do 1 over x dx here, and this is a less apparent u substitution. You're picking u to be in the denominator, and then you rewrite that in terms of x, and go from there. But I don't know something necessarily that I differentiated, I get this, at this point. So today, the first thing I want to start with is 5.4. And I think it's going to make sense. This is how integration was developed. This is how it all started. We wanted to find the area underneath the curve. So we're going to skip through some of the summations for a minute. So we wanted to find this area underneath this curve. We originally, in the past, we've taught 5.4 and have homework problems over it. However, this semester, since a couple classes had 3 snow days, we have to cut something out, and this is one of the sections that if we don't have time, we're cutting. So this won't be on the final exam in this aspect, where what we're going to end up doing is saying, okay, I don't know how to find the area under this curve because I can't graph it. I can't see, I can't decompose it into rectangles and triangles. But what I can do is say, okay, this is a kind of like a rectangle, and I can either make it a rectangle by taking the left endpoint, the right endpoint, or the midpoint. And I can add up the area of each rectangle by using algebra. If I take the sum, if I have 10 rectangles, if I take the sum of the area of the 10 rectangles, I get an approximation of the area. Right? So Wiley actually has a pretty nice applet here in Wiley. If you go to the calculus applets for chapter 5, go ahead and put a full version here. Let's look at the function t squared. So you guys know what the function t squared looks like, right? And let's say I want to find the area underneath the curve from 0 to 2, since that's what's in my, let's say T max is 16. X max would be, let's see if I can zoom in a little bit here. Okay, so this is the x squared, right? Let's see if I can move this.
Change that x range.
So T min, T max. Let's see, let's put it at 10. Okay, so let's put it to 5. Does that make sense? This is the point 0, 0. This is the 5. So if I plug in 2, I have 4. If I plug in 3, I have 9. So if I want to integrate this from 0 to 3, and let's say I have these rectangles. And what I want to do, each one of these thicknesses is a delta x, which is a differential length. And that's kind of where this dx comes in from. So before we've said, okay, here's the integral sign and here's the dx. We never explained where this came from. It was just like, this represents being able to find the antiderivative. So if you differentiate a function and you integrate it, you get the original function. But now this section is to explain where the dx comes from, and it comes from this delta x. So I can break up this area underneath this curve into subintervals or intervals, and let's say I break it up into 3. So it depends if I want to use the left endpoint, the right endpoint, or the midpoint. So you can see if I use the right endpoint, I get an overestimation. What that's saying is, if my interval is a length of 3, I divide by 3 and say I take the point 1, the point 2, and the point 3. If I plug in 1 to the function, my height is 1. My thickness is 1. So the area of this rectangle is 1 by 1. If I plug in 1 in this function, my height, or if I plug in 2 in this function, my height is 4. So this area is going to be 1 by 4. Right? This is an overestimation. But if I take the number of rectangles to go to infinity, you see how I get a better and better approximation? So here if I start, it's a large over approximation. And when I take the limit, and this is going to be noted as the limit as the thickness of these delta x's go to 0. Right? And if I do that, I get a better approximation. You can see here the shaded region goes from 27 to 9.1. So the closer and closer, the larger intervals I can put in, the better area I'm going to get. So you can see it's not even really above the line. But for me to add up 1,000,000 different rectangles is going to take me forever. So there's also the midpoint, where you take the length of the interval, divide it by 2, and take that midpoint, and that's generally a better approximation than a right endpoint or left endpoint for smaller numbers. But that's kind of the idea of what we're doing here. Where did the reading content?
For 5.4, there was a few written problems. Are we not going to have
You
those?
don't have to do those, no. 5.4 is just cut out on the homework. There was 2 written problems, and one of those will probably take you 30, 45 minutes to write it up.
Oh.
And I'll show you how that goes about in this example here. So I'm looking for the area, and this represents, this is the sum of k equals 1 to n of the function f of kx star. So that depends if you're doing the right endpoint, the left endpoint, or the midpoint. If I plug in xk into my function, that gives me the height of any k rectangle. Right? So I have k rectangles here, or I have n rectangles, and k is any general one. So at the kth rectangle, the height would be represented by f of xk star. Then I take it times the thickness, right? So if k is 1, that's the first rectangle. So I plug in the height of the first rectangle times the thickness, that's the area of that rectangle. You guys see that? And I go through until I get to n. And if I take the limit as the thickness goes to 0, that's also the limit as n goes to infinity. That would give me the exact value for the area underneath the curve. Just a comment. In the past, we've gone through and taught this section, and we do an example that starts like this. We want to find the area of this ellipse type thing, or what do we get? We get actually, this is a circle that's shifted a little bit. And we're using a midpoint approximation. So we have to get a representation of the function, which is 9 minus x squared. So I have 9, each point is going to look like a function of k and n, where k is the kth rectangle, and n is the limit as n goes to infinity. So we go through, and it takes about this much space, and you see a lot of algebra here, to get 18. 5.5, which I'm going to touch on today, is using graphing this to find the area of a semicircle. I can find that by plugging in, being able to graph this. This is a circle centered at 0, 0 with radius 3. 0, 9. Is that quite it? But we're going to learn that this eventually transforms into calculus instead of algebra. So we're not going to touch on the algebra this semester. We're going to focus on the calculus. So going back to 5.5, here we have that the definition of area is represented by this limit as the number of rectangles go to infinity of the sum of the area of each rectangle, right? So sometimes this notation is a little what's going on there. So do you see that this is the height of the rectangle, and this is the thickness of the rectangle? So that gives me the area. I'm taking the sum as 1 goes to n, and then the limit as n goes to infinity.
So is that something we should memorize?
No. So they do an example with x squared. And you can see this is algebraically intensive. I'm not going to have you pull this out of thin air. We're going to focus on being able to calculate the area from 5.5. So this is the example I was talking about, left endpoint approximation, right endpoint approximation, and the midpoint approximation. If you take the limit as n goes to infinity, they will both converge to the actual area underneath the curve. In this example, this might be an overestimation, this might be an underestimation, this might be a closer estimation. But it's still just an estimation. This is the example that I usually do in class. And you can see if you do a left endpoint approximation versus a right endpoint versus a midpoint, you can see how close they are, but this one, what did we get the answer to be? I think we get 18. So this one is over, this one is under, and this one's closer. But that's just with 10 rectangles. But if I have to find the area of 10 rectangles and add that together, it gets cumbersome. Especially if I don't even know if I'm over or under or what's going on there.
Can you just generally accept, though, that in any given area that you're trying to find, the midpoint would be the closest?
Yes, the midpoint is the closest. And you can see it gets 10, 20, 50, it's even closer, right? This one still is under and this one's still over. So net signed area takes this into account because the height of the rectangle would then be negative. So I'd be adding a negative number. So here what the net signed area is going to come in effect when we look at really 5, if my function is above the x-axis and I find that area, that's positive area. If the function is below it, it's a negative area. This net signed area is also represented here. So it doesn't matter. If I have a function, and let's say I have a function that looks like this. And I want to integrate from A to B. I take this triangle plus this triangle minus this triangle. And I would get the area under the curve from A to B. So it's kind of nice that this takes it into account. This is the example. If I want to find the area underneath the curve x minus 1 from 0 to 2, take the area of this triangle plus the area of this triangle. And it turns out to be 0. So you can have net signed area be 0. The area underneath this curve here is 0. Don't worry about anything like this. So in chapter 5, in the homework, 5.5 is what we're going to focus on today, and this is the wrong. I'm not going to have time to really cover this because I want to give you your quiz, so I'm going to push 5.5 back to do next Monday because I won't have the time to lecture on it. The amount of time I want to lecture on it. But 5.5 is then the step between the summation formula and the integration formula. They all represent area. So it seems, do you see the function here? Let me zoom in a little bit. What is the function? I take 11x times the quantity 1 minus 6x. This delta x is a differential. This is the length of my kth rectangle. So if I want to change this into an integral, if I want to change the summation from minus 7 to 5, I'm going to integrate from minus 7 to 5 the function dx. This dx comes from this differential. When I integrate it, it turns into a dx. So the correct answer here,
The delta x becomes a dx?
yes,
Okay.
because it's the differential. So that means what's the thickness of my rectangle. So the function is 11x minus the quantity 1 minus 6x. So this is the only one that has that. If I want to find the area from minus 7 to 5, I integrate from minus 7 to 5 of 11x times 1 minus 6x dx. Right?
This is notation, the 5 and 7.
Yes, this is just notation. It's changing all the xk stars to x's and changing the delta xk to dx.
I was talking more of above and below the integral sign.
This? Yeah. This is a notation of this is the left endpoint and this is the right endpoint. So I'm integrating from minus...
Yeah, you put the smaller one on the bottom.
Yes. So I'm integrating from minus 7 to 5 of this function. Now, this is not saying we know how to find the area yet, because we don't. This is going to be a quadratic where we'd have to complete the square to learn how to shift it. It would be a mess to try to find the area. And we don't have any techniques up until this point to find this area. That's going to happen in 5.6, which is the fundamental theorem of calculus. So this would be the answer here. I think let's go ahead and write this one up, and you can see how this area comes in. And really this is 5.5. And I want to go ahead and write one comment before we start this. So 5.5 is the definite integral. And let me see where I want to start. Definition 5.5.1 in your book says that the area can be represented as the integral from a to b of your function dx, which can be represented as the limit of the max delta xk's go to 0 of the summation k goes from 1 to n of f of xk star delta xk. So what this picture means, if I have a graph of some function, and I want to integrate it from a to b, then there's some rectangle in here. This is xk star. The thickness of this rectangle is delta xk. The height of this rectangle is f of xk star, right? If I plug in xk star to my function, I get the height. Either a left endpoint or a right point or a midpoint, it doesn't matter here. So then if I add up all the rectangles and I let this differential length go to 0, if I let delta xk go to 0, I end up with this integral of the function times times dx from a to b.
What's the symbol above the K?
Star. This is the notation your book uses. It's saying, and really there's also a star here, because what they're saying is your grid size doesn't have to be uniform. You could have a grid size that is uneven. So I could have a grid size, I could break it up like this. And add up the area of each one of those rectangles. So if I let the maximum delta xk go to 0, then all the other ones have to also be 0. Right? Typically we use the uniform grid size because it's easy to calculate. If my interval I'm integrating over is 10 units, then I can break it up into 10 subintervals, and each one a length long, or 9 subintervals, each one a length long. Or I can break it up into 50, then I would say 10 divided by 50, so then I would know what each length of a subinterval is. But you don't have to. You don't have to have it uniformed. So that's why you take the maximum of the thickness of the kth rectangle, go to 0. Question?
On the top there, where of the picture, we've got f of xk star.
Yes.
Is that the function for the line that's the top of that rectangle, or is that the identification of that? Like,
That's fk star is this point.
oh, okay. So
It could be a left endpoint, it could be a right endpoint, it could be a midpoint. It's just the height of the rectangle.
Sure.
Depending if I'm doing an endpoint approximation, a right endpoint, a left point, or a midpoint. We don't want to focus on too much of
Sure.
getting into that because it's very cumbersome to algebraically.
Is this something that, like, at least as far as like an actual application later on, would that be like for analog to digital conversion, or getting a square-shaped wave out of a?
This application is area underneath the curve. No one does it this way.
Okay.
We always use fundamental theorem of calculus. You can do it algebraically, and before we had the fundamental theorem of calculus, the only way to approximate it is algebraically. So here I could do an approximation by breaking it up into rectangles and adding them up. But it turns out the fundamental theorem of calculus is going to be a lot stronger. And what would we do in 2 pages, algebraically, we can do in 2 lines using the fundamental theorem of calculus. And the fundamental theorem of calculus also takes in account the net sine area. So you don't even have to care if it's above the curve or below the curve. You're just doing the fundamental theorem of calculus. Okay, so this is the area. 5.5, so in the last 2 minutes here, because I want to give you time for your quiz. 5.5 is all about graphing. and finding the area. Let's see. And finding the area of under the curve. So an example from Wiley. This is 5.5 number 17. I have this function f of x equals the absolute value of x minus 18 if x is greater than or equal to 0, or x plus 18 if x is less than 0. This is the only type of problem where the fundamental theorem of calculus, well, that's not necessarily true. This is one type of problem where the fundamental theorem of calculus is going to be harder than graphing it, because you have to take this absolute value. So if I graph this, at x equals 18, that means x is greater than 0. At 18, it's 0, right? If I plug in 0, this is saying x equals 0, I use this function. If I plug in 0, I get the absolute value of minus 18. So this goes to 18. If I plug in minus 18, I get 0 again. Right? So I know in this interval, my function's always positive. Because here it's always positive. Sorry, no. Here it's always positive, right? So from x being greater than or equal to 0, from 0 to 18, I'm decreasing. And then from 18 on, I'm increasing. And I have a slope of 1. Here, at the point x is minus 18, my function is below the x-axis. So this is x equals 18. This is a height of 18. So if I wanted to find the integral from minus 18 of 0 of f of x dx, what would that be? Yeah, so that would represent this specific triangle, right? So this would be the area from minus 18 to 18, which we would know to be 256 divided by, so we get 162. So we take 18 times 18 divided by 2, because this is a length of 18 and a height of 18, right? If I wanted to find the integral from minus 18 to 18 of f of x, I would have 324, because that would be 18 times 18 over 2 plus 18 times 18 over 2, or 36 times 18 over 2. Right, if I say that the base is 18 plus 18, it would be 36, and the height is 18 divided by 2. Multiple ways to look at it. So that would represent these two triangles. And then on Wiley, there's a couple more where you go from like minus 20 to 22. So be careful. If you're going to plug in minus 20, minus 20 plus 18 is a minus 2. So this is a circle. This is a triangle that has an area of 2, but it's actually minus 2 units. So I would add that to, I would take a positive number minus this to get the area from minus 20 to 0, or from minus 20 to 22. Does that make sense? All right, we will finish up this section on Monday. I'm going to change the Wiley date to be due a week from Monday, because you don't have that much time to work on it since I just lectured over it, and give you your quiz.